What's going on, everybody? In this video, we're going to be talking about indefinite integrals. Now, for most of the time that you've been in calc, you've been talking about derivatives, right? You've been starting from a function f, you take a derivative of it, and you get a function f prime. But here's a question for you. Can you start from f prime and work your way back to f? How would you get back there? How would you reverse that derivative? Well, that's what an integral is, and that's what we'll be learning about in this video. So for this video, I have the timestamps listed on the left here, and I'm going to just go through the notes here real quick in a couple minutes and talk about the different topics that we'll be covering in this video. And so we'll be starting with an introduction, and I just want to talk a little bit more in this section about how an integral is kind of reversing a derivative. We'll just get a little bit into more depth there. And then we're going to be getting into the notation and the nomenclature of derivatives and integrals. I want to show you how the notation for integrals is different. I want to talk about the different pieces, and I want to talk about the nomenclature, right? How we name the different stuff with integrals, right? I want to talk about the verb, like all that, because for the longest time, I didn't know, like I know we say taking a derivative. I wasn't sure if we could also say taking an integral, or if we could always say integrating. I wasn't sure about the difference between an integral and an antiderivative. So I just want to clear all that up for you so you don't have to, experience that same thing. And then we're going to be talking about reverse power rule. Now, with derivatives, the first rule that we learned of how to take them is with power rule. And so if we want to start reversing derivatives, we should probably start by reversing power rule. And that's exactly what we'll be doing here. I'm going to take you through just reversing the derivatives of these guys. And from there, we'll be able to create our own rule that reverses power rule. Then we'll be getting into some integral properties, and I promise these won't surprise you at all. Right? I talk about the derivative properties right here, the constant multiple rule, right? You can pull a constant out of a derivative. And also the sum and difference rule. You can, if you have two functions being added together and you're taking a derivative of it, you can just take the derivative of those guys separately. I mean, it's the same thing for integrals. That's basically what that section is already. Then we'll do some practice, just taking some integrals there. I'll talk about your integral table, the different integrals that you should memorize and all that. It's really not going to surprise you again. I mean, for taking a derivative of sine, we know that's cosine. And so here you see that the integral of cosine is sine. And so this integral table shouldn't be nearly as difficult to memorize as the derivative table was. It's just thinking about derivatives in reverse, and that's it. Okay? And then we're going to do some more practice with that, and that'll be it for the video. All right, so that's all coming here, and I do have both the unfinished and finished notes available as a PDF in the description. Now, before we get into this video, I quickly wanted to mention my full Calc 1 course, which I'm going to have linked in the description down below. In this course, I have plenty more practice problems to really get you feeling confident with each topic. I also have video explanations for every problem in the course, so don't worry, you won't be left in the dust on anything. And so if you're interested in that, be sure to check out the link in the description down below. Now let's get into this video. So I'm going to start off here with that introduction. I just want to, again, talk a little bit more about how an integral reverses a derivative. I want to talk about the key terms here, what inverse operation means, and I'm going to tie it in to inverse functions. So let's say that we have a number 4 and we add 2. How do we undo that? Well, to undo us adding 2 to 4, we subtract 2, don't we? Right, and so this subtraction undoes the addition. So what we would say there is that subtraction is the inverse operation of addition. Okay? It does the opposite. Division is also the inverse operation of multiplication. Right? It's an operation, it does something, right? Subtracting 2 is an operation, and it's the inverse. So it does the opposite of what adding 2 would do. Now, when you studied inverse functions in algebra, you were looking for a function f, and it would have like a little -1 up here, and so it'd be f -1 of x. And that function is what it was actually meant to do, which honestly, I don't think I knew at all when I was in algebra. I just was like, all right, why do we care about this inverse function thing? And so that's why I want to tie that in all right now, and then that's also going to help you understand what integrals do. So we would try to find this function f inverse, and this function would undo all the different things that happen to x when it's plugged into f of x. For instance, in f of x right here, you can see that this x gets multiplied by 2, and then you have a subtraction of 5, right? You have that 5 there. And so what an inverse will do is it'll take away that minus 5. It'll, add your 5 back, and it'll also, instead of multiplying by 2, it's going to divide by 2. And so we just need a function that'll take this function and give us back our x value. So how do we find that? Well, what you would do in algebra, real quick here, you would have y equals 2x minus 5. You would switch the x's and the y's, and then you would just solve for y. So you would add 5 on both sides. You'd get x plus 5 is 2y. You'd divide by 2 on both sides, and you'd get that y is x plus 5 over 2. And so what you would say off of that is that your inverse function is 1/2 of x plus 5 halves. Right, just splitting that fraction up. And so, well, how can we, I talked about how this inverse function reverses all the things that f of x did to x. How do you actually write that? How would you show that? Well, what you would do is, we know that f of x is 2x minus 5. And what we're going to do is we're going to make f of x go inside of f prime of x. This guy is going to be the input of f inverse. And so what we would do, we know that f inverse is 1/2 times x plus 5 halves. So we'd have 1/2 times, instead of x, right? Now we have a f of x. And so we put that in there. And well, what is f of x? F of x is 2x minus 5. And so let's plug that in. And so when we do that, you can see that we get, well, you have a 1/2 times 2x, that's going to give you x. And then you have a 1/2 times negative 5, that gives you negative 5 halves. Add 5 halves to that, and you get 0. And so what ends up happening is, when you take the inverse of that original function, right, when you have that inverse function and you have your input be that original function, right, it reverses all the things that you just did to it, and you end up back with that x. That's the equivalent of us starting from f, taking a derivative, getting the f prime, and then we take an integral to get back to f. I just thought that was a really neat parallel because, of course, you're going to need to know about inverse functions, especially for going into physics. When you talk about linear algebra, you need to have an understanding of what all that stuff is. So I thought this would be a neat tie-in. Cool. So here we go. The question is, what's that inverse operation of taking a derivative, right? How do we undo that? And of course, here I talked about how that's integrating. So we'll be getting into how to take the integral in the yellow section. Now, real quick, we want to talk about some different notation, nomenclature, all that. For derivatives, the main thing that you probably said when we were taking a derivative, right, is we're taking a derivative, right? Sometimes people will say we are differentiating. That's probably the more correct term to use, but no matter. You can also say that we are going to take an integral, right? That means we're reversing a derivative, or the more correct version is we are integrating. Okay? And then you have your operator symbol, right? Whenever we saw a d over dx on something like you see down here, that means we're taking a derivative of that thing. Here we're taking a derivative of that x squared. Okay? Now, and this x would tell us what variable we're taking a derivative of, right? Here we're taking a derivative of x, so that's going to give us 2x. Now, with integrals, our integral symbol, the operator symbol, is this little squiggly guy, right? It's this like elongated S looking thing. And how we write this, there's a couple different parts. It's a little more complex than what's going on here, but really not by much. So here, let me draw here, and that's my highlighter. Okay, so this right here is called your integral symbol. Okay, and I talked about that. It's, your integral operator. It's telling you you're taking it into integral. Now the thing that is smushed in between the integral symbol and the dx, I'm talking about this 2x right here, we call that the integrand. It's the thing that you are integrating. Okay, that's the equivalent of this x squared here. That would be the equivalent of the integrand. Okay, and then you have this dx over here. Now this dx, we call that's a differential, right? We've talked about differentials with derivatives. It's just that little change in x. That's the equivalent of this dx down here, right? It's telling you, in this case, all I would say is just think about it as the variable that you are integrating. Right here we are integrating x's, right? Yeah, here we have a 2x, that makes sense. Okay, and then what you get over here is your finished integral. Or you can call that an antiderivative. Now, I do want to note that might seem a little confusing to you. This right here is an integral, or you could call it an antiderivative. That's also what this is. These things are equal. They're the same thing, right? This is what you probably think of when you think of an integral, but this right here is your, I guess you could say, your completed integral. Okay, just as you would say that this is your derivative, right? But this is kind of your incomplete form of the derivative. You still have to take it yet. Okay, so it's the same thing here. And that's, I think, something that I got a little caught up with as far as the naming goes. But yeah, that's what I would say on that. Okay? Awesome. Let me get back my color here. So now we're going to move on to reverse power rule. And I want to start off simple here. Okay? I just want to try to undo power rule. That's going to be the first step if we really want to start reversing these derivatives. Let's start from square one. Let's start reversing power rule. So let's think about it here. What's the integral of x dx? What that means, again, is that we are trying to reverse the derivative that's been done to get x. And another way to say that would be the derivative of what is going to give us x. That's what this thing says. Okay? And so, well, let's answer that. The derivative of what gives us x? Well, let's think. If we have the derivative of, let's say the derivative of x squared, we know that's going to get us down to like an x, but there's going to be a 2 in front of it, right? So how do we fix that? Well, we can take the derivative of 1/2 x squared. Right, oops, sorry, that's the wrong notation. Derivative of 1/2 x squared. And now we just get x, right? That 2 comes out front, it cancels out with the 2 in the denominator, and you're left with x. And so what we say here is this integral is equal to 1/2 x squared plus c. Why am I putting a plus c here? That was something that everybody, we saw that plus c, we were like, what are you doing, right? When we were in calc. Let me talk about why that plus c is very necessary. Well, the derivative of 1/2 x squared, we know, is x. But let me ask you this. What's the derivative of 1/2 x squared plus 1? That derivative, the 1 goes away, right? This is also x. And so when you reverse this derivative that's been done on x, you don't know if you started out with a 1/2 x squared, or if you started out with a 1/2 x squared plus 1. Or for that matter, you could have any constant on that end, any number that does not have an x on it, right? That's what I'm calling a constant here. And that is where c comes in. C represents that extra constant that needs to be accounted for. You could have any number here, and you would still, when you take that derivative, end up with x. Okay, so that's why the plus c is there in the first place. So let's move on here and let's reverse the derivative done on x squared. So again, how do we say this? Well, the derivative of what is going to give us x squared? Well, let's think. We have the derivative of x cubed. That's going to equal 3x squared, and that gives us the x squared piece, but we have that 3 out front. That's got to go away. And so what we can do is multiply each side by 1/3. Or you could also think about it as taking a derivative of 1/3 x cubed. And what that does, again, the 3 is going to come out here. It's going to cancel out with that 3 in the denominator, and you're just left with x squared. And so here we write that this integral is 1/3 x cubed plus c. Now already you might notice a pattern, and you might understand already kind of what we're doing with the reverse power rule, but I'll do one more example here and then we'll really start to see this pattern come out. Okay, so let's do this integral of x cubed dx now. Well, the derivative of what equals x cubed? Well, you could maybe already think about this. The derivative of, x to the 4th, but that was going to give us a 4 out front. We don't want that 4 out front, so we're going to divide by 4, or multiply by 1/4, same thing. And that'll give us our x cubed. And so what happens here is this ends up being 1/4 x to the 4th plus c, right? And so what would you say this would be? Well, it would probably be 1/5 x to the 5th plus c. Notice how all these powers are increasing by 1, right? You take this original power, 1, 2, 3, 4. You increase it by 1, so instead of 1 we get 2, instead of 2 we get 3, 3 goes to 4, 4 goes to 5. And that power that ends up here also comes out and becomes a denominator. And so you see that pattern unfold. So what would you say would happen if we integrated x to the n, right? Where n is just any power, right? It could be 2, it could be 3, it could be 10, it could be -2. What happens to that? Well, let's see. First off, that n is going to increase by a power. It's going to go to n plus 1, isn't it? I mean, say n was 4, n plus 1, which would be 4 plus 1, and that's 5. So we're good so far. We have it x to the n plus 1. Now out front we have that fraction, and that's going to be 1 over, it's that same number that's in the exponent, so it's going to be n plus 1. Right? And then we just add that c on the end. What we've just done here is come up with the reverse power rule. That's exactly what that is. And I have that written right here. Now, I do want to note here with this whole reverse power rule thing that this is only going to happen where n is not equal to, this shouldn't say 1, this should say -1. Okay? N cannot equal -1 here. And you can see that, right? Let's talk about the integral of x to the -1 dx. For this integral, well, what is x to the -1? That's 1 over x dx. And if you use the reverse power rule here, remember you increase that power by 1. And if you increase -1 by 1, you get 0. And so you get x to the 0, the x goes away because x to the 0 is just 1. So what actually is the integral of 1 over x? The derivative of what gives you 1 over x? Well, that's natural log, right? The derivative of natural log of x is 1 over x. And so we say that the integral of 1 over x dx is natural log of x plus c. And actually, we end up with absolute values here. Okay, but that's another story. Okay, awesome. So that's reverse power rule, and now let's get into those integral properties. Now, again, I mean, these are not any different. I'll just go over them again here. I pretty much did them justice in the introduction here when I was going through everything, but we had properties for derivatives. It's the same thing for integrals, right? It's the same idea for these two. Now, of course, there is more properties that we can talk about with integrals, but I'm not going to mention them in this video because they're for definite integrals, which is something different. These are called indefinite integrals. You'll know something's a definite integral if it's got numbers on the integral symbol. Okay? But yeah, so the first property we'll talk about is the constant multiple rule, right? And we were saying if we take a derivative of something like 3x, we can take that 3 out. The 3 doesn't play a role, right? And we could write this thing as 3 times the derivative of x, right? Just pull that 3 out, and we know the derivative of x is 1, so this is 3 times 1. So we can do that, and we can pull that constant out for integrals too. It doesn't really do anything special. Of course, then you have the sum and difference rule, and that was saying, well, if we have a derivative we're trying to take of 3x plus 2, how do we do it now that we have two things being added together, not just one piece? Well, we can take the derivative of each of these pieces separately. We take the derivative of this thing, add it to the derivative of this guy. That's the same process for integrals. If we have the integral now, the integral of 3x plus 2 dx, we take the integral of this piece using some reverse power rule, and then we take the integral of this piece. Again, that's reverse power rule. You can think of that 2 as being 2x to the 0 power. Okay? Great. And so that's really what we'll be doing practice with that right now. Okay? So let's start off with that practice here. Now, we want to integrate x to the 6th minus 2x to the 5th minus x to the 3rd plus 2/7 dx. So first off, I'll break this up with properties just so you can see it, but really I try to think about it all at once. Okay? So you have the integral of x to the 6th dx minus 2, right? You can just integrate this piece, and then integrate this piece, and then integrate this piece, and integrate this. Okay, and each, of course, is going to have their own separate dx, right? That's just part of the notation of the integral. So you're going to have minus a 2 integral of x to the 5th dx, right? We can bring that 2 out front of this integral. If you actually wanted me to write that out with an extra step, I would have said that it was negative integral of 2x to the 5th dx. But again, this 2 is just a constant. We can bring it outside and have that be a negative 2. Okay? And then we have minus the integral of x cubed dx. And then we have plus the integral of 2 over 7 dx. Okay, which you can, if you want, write this as plus 2 over 7, the integral of dx. That's fine too, right? 2 over 7 is technically a constant on that dx, but yeah. So that's great. Now we can integrate. So let's start off with this x to the 6th. Integrating x to the 6th is not going to be that bad, okay? We're just going to raise the power by 1 from 6 to a 7, and then we bring that power out front and we flip it. So instead of a 7, we get a 1 over 7. Okay? Another way that I like to write this, just to prevent a fraction being multiplied by like the x, I just don't like seeing it that way. I just write x to the 7th over 7. Okay, so if you see me do that later in the video, that's all I'm doing. So then we're going to have minus 2 times the integral of x to the 5th. So we raise the power by 1, bring the power out front, and flip it. Okay? And by the way, yeah, I'm not adding the plus c's on the end because I'm just going to do that all at the end. I'll just do, blah, blah, blah. Here's the rest of the integral, and then I'll do plus c. Right? I can add little constants here like c1, c2, c3, and c4. Right? But if you add up a bunch of constants, like 2, 3, 4, whatever, you just get another constant. It's just another number that does not have an x on it. So I'll do the plus c all at the end. So now we're going to subtract the integral of x cubed dx. And so we raise the power by 1, bring it out front, and flip it. And then lastly, we just have a 2 over 7 times the integral of dx. You can think of this guy as being an x to the 0. And so raise that power by 1, giving you an x to the first power. Bring that 1 out front and flip it. I mean, that's just going to still give you a 1 over 1, right? I mean, 1 is already 1 over 1, right? That's the same thing. But if you flip 1 over 1, if you take it and you go like this, it's the same thing. So that's why I've got a 1 over 1 here. Okay, and here you should be able to see the integral of dx just ends up being x. Okay, that's all. That's just something you should know for future reference. Okay, I just figured I would do it all out with you right now. So let's simplify this a little bit. We're gonna get. I'm just gonna write it like I like to see it. X to the 7th over 7 minus, we have a 2 times 1/6, that's going to be a 1/3. So we get x to the 6th over 3. And this has got to get a plus c. Don't forget your plus c's. Minus x to the 4th over 4 plus 2 over 7x, so 2x over 7. And that's got to have a plus c. Okay? So that's all fine and dandy, but what if we had an integral that looked like this? Well, how do we, I mean, that doesn't really look like something we could do reverse power rule on right now, but how do we make it something that we can do reverse power rule on? Well, remember something that we know about fractions, right? We can split this guy up because we have multiple terms in the numerator. And so we can write this thing as the integral of 1 over t plus rad t over t plus t over t. And you put that thing in parentheses here. Sometimes you'll see these integrals without parentheses here. It'll just be like that. I mean, that's just laziness. I sometimes do that as well. I do that all the time, actually. So if you see that, just understand where that's coming from. So from here, we're just going to simplify these two guys, and then we'll be ready to integrate. And so when we do that, we get the integral of 1 over t plus, well, what's rad t over t? Well, rad t is t to the 1/2, and t is just t to the first power. And so if we subtract those two powers, we're going to get t to the negative 1/2, which is 1 over rad t. Okay, that's something I would just try to remember. Okay, if you have a rad t and a t, or a rad x and an x, it's just it's just going to kind of switch the place of the radical. And so it starts at the top, it ends up at the bottom. I don't know. That's just kind of how I think about it sometimes, but you'll see that a lot. And so you get 1 over rad t here. And then lastly, you're going to get a 1. So combine all those, you got a dt there. And now we're ready to integrate. So the integral of 1 over t is first, and we know that's natural log absolute value of t. Okay, I mentioned that earlier. And we're going to have absolute value signs on there. Okay, that's just something that we do to prevent us from getting negatives or stuff like that inside the natural log. Okay? And so then, what about the integral of 1 over rad t? Well, what I would do for that is I would memorize that integral for sure. That's something I'll mention in the next section. That's a 1 over t to the 1/2, right? That's what 1 over rad t is. And so that is a t to the negative 1/2. So we can apply reverse power rule on that. So this becomes we raise the power by 1. So negative 1/2 plus 1 is 1/2. And then we bring this new power out and we flip it. Well, 1/2, if you flip it, is 2. And so we get a 2 rad t. That is what we're going to put here, and that's something I would try to tell you to memorize because this integral pops up all the time. And so I've seen it, hundreds of times. So just integrate this to 2 rad t and you're set. Then lastly, we get the integral of 1. The integral of 1 is just going to be t. Okay? I mean, think about it. The derivative of t is just going to be 1. Derivative of x is just 1. Right? So then we have our constant c on the end, and that right there is our finished integral. Okay? Awesome. So now I'm going to move on to the integrals to memorize section. This is your integral table. I'll zoom out in a second just to give you a full ability to screenshot this. I just want to make sure that I add a couple things first. So the first 3 integrals that I'll talk about here, they're going to be pretty simple for you. This integral we've already talked about, the integral of having some constant here, right? We're just going to put on an x. That's like saying the integral of 3x dx. Okay, this is 3 dx. This integral just ends up being 3x plus c, where 3, I guess, would represent the k here. Okay, that's just thinking about that as a 3x to the 0 dx, because again, this is 1, and then you do reverse power rule on this, and you'll see that the 3x to the 0 becomes a 3x. Okay, that's your first little guy there, and then you have things like the integral of e to the x is e to the x, and that should make sense to you because the derivative of e to the x is e to the x, and so the integral of e to the x should be e to the x, right? The integral is just the reverse. We already talked about this integral. Then you have your trig integrals over here, and again, these are just going to be the opposite of what you've already dealt with. If you think about these as being your derivatives over here, yeah, you would get these guys. Like, again, the integral of cosine is sine because the derivative of sine is cosine. The derivative of tangent, this is missing a plus c, the derivative of tangent is going to be secant squared. So the integral of secant squared is going to be tangent. And so on and so forth. It's the same idea. And then, of course, this is an integral that you see quite a lot, actually. The integral, if you ever see a 1 over 1 plus x squared, that's arctan. Right? So that's just something to memorize there. Now, other than these, there are 2 that I would say to memorize, not because you have to, but just for convenience. The integrals that I'm talking about are the integral of negative 1 over x squared, or actually just the integral of 1 over x squared dx, and the integral of 1 over rad x, which is something that we've already talked about. First, the integral of 1 over x squared, this guy, well, this is just a x to the negative 2, and when you raise the power by 1, you get a x to the negative 1. Bring it out front and flip it, that's just going to be a negative 1 out front. So that's a negative 1 over x, and so that's what this ends up being. Now, you'll remember that this derivative is something I already told you to memorize. The derivative of 1 over x, I said, was negative 1 over x squared. That's something that you should remember because it pops up a lot when talking about derivatives. Now we're just saying the opposite, and the integral of 1 over x squared tends to pop up a lot, and you really don't need to go through all the trouble of doing reverse power rule if you can just memorize that since it pops up so much. Another integral that pops up a lot is this integral of 1 over rad x, and we said that integral is going to be 2 rad x. And of course you add your constant c. And when you combine all those guys, that I would say is a pretty decent integral table. Okay, and I did go down a thickness in my pen, so I gotta increase that. There we go. Now it'll match all the others now. Cool. So there you go. There's your integral table that you can take a screenshot of, and yeah, that's gonna be really, really nice to have. So now let's move on to our practice. We have 2 quick practice problems here, and that's gonna do it for this video. Okay, we'll start off with this integral here. We start by integrating x squared. So the integral of x squared is going to be, well, let's raise that power by 1. Let's bring that power out front and we flip it. Great. Then we add the integral of 1 is just x. Again, think about it as the derivative of x is 1. And then you get this 1 over x squared plus 1. Like I said, it pops up all the time. That guy is arctan. Then you, of course, add on your plus c there. Please make sure to not forget your plus c, or else you will get the problem. You'll get points off. You just promised me, all right? Because I forgot my plus c all the time when I was in calc. It was such a bad habit of mine to start off with. It was a bad habit of a lot of other people in the class. And the plus c is actually really important when you're solving like things like differential equations and all that, which is a whole nother topic. But yeah, so remember your plus c. That's all I'll say. Okay, so we did that integral. Now we're on to the last one here. Here we have the integral of secant times secant plus tangent. And here's a great example of an integral that's not always going to be just, oh, you integrate this thing, you integrate this, and then you integrate this. Okay, this integral is something that has things being multiplied, and so I think we should distribute here. Okay, and then we can see about solving the integral just like this. So distributing through, we get a secant squared of x plus a secant x times tangent x. And that's going to go right here. Okay, and I'm going to put brackets on the outside here. Okay, I'm using brackets here because I already have parentheses inside, and so it'll just look really gross if I use more parentheses. And now, well, what's the integral of secant squared? Well, let's think about it. The derivative of what gives us secant squared? That's tangent. The derivative of tangent is secant squared. So the integral of secant squared is tangent. And then the integral of secant x tangent x is going to be secant x. The derivative of secant is secant tangent. And that right there is your completed integral. Okay? Awesome. And yeah, guys, that is going to do it for this video. I hope this was able to help you, leave any questions that you have in the comments. And of course, if you're interested in that full Calc 1 course, be sure to check out the link in the description down below. I'll have plenty more practice problems for you and I to go through together, just so this really becomes, concrete in your head. Okay? So that's it for me, guys. I'll see you soon.